Okay. You guys see this okay, the screen? All right. I'm assuming you guys are good. So again, this is very conceptual. So I'm hoping you're caught up on watching the videos and we're reading the book. So let's explain what these symbols mean real quick, just in case you haven't. So last time we said the limit as x approaches some number. If we have a plus sign, they're talking about that specific function approaching that value from the right, right? So C plus. So approaching from the right, right? And getting closer and closer to, right? To 3, the y value. So as the x's get closer to 6, the y values get closer to 3. And that's all we're doing. So from the right side, it is 3. So we put 3 here. From the left side, it turns out to be the same, approaching 3, right? And if both directions is the same, then you say, yes, the limit exists and it's equal to C. Sorry, equal to that y value. So that's stuff we talked about last time. So it's a good, can rehash this really quick. You guys remember and understand that idea? Okay. Continuous is something new. Cool. So that we're going to need a formal definition because it's a little different. Give me a sec. Let me pull it up. I might have it in my notes, actually. One moment. Here we go. Let me write it down on paper. So this is 2.4. Continuity. And one-sided limits. So we just talked about one-sided limits. Now let's talk about the definition of continuity. What does it mean to be continuous at a specific point? The formal math definition, of course. So all these three conditions must be met in order for a function to be continuous at a point C. Okay. So let's write this in English first. A function f is continuous at C when the following conditions are met. And there's 3 conditions here. Number 1, f of C is defined. That means you can plug it in and you get a value at C. So that must be true. Number 2, the limit of the function as x approaches C exists, meaning it's the same from both sides, right? If it exists, that means it's the same from both sides. That is to say, the limit of f, x approaches c from the plus is equal to the limit of f of x, x approaching c from the negative, right? This is the Latin abbreviation, right? It est, meaning that is to say this. This means this. If the limit exists, this must be true. Number 3. The limit of f of x is equal to, as x approaches c, the functional value at c. So if all these threes are met, then cool. Right. There's a quick note here, in case it wasn't already clear. If the limit from the right is not equal to the limit from the left, then the limit of f as x approaches c does not exist. Okay. And that's basically what this is saying up here. Does that make sense? Are these three things clear to you? Do you see what these mean? If they are clear, then you're not BSing me. Is it continuous at C? Did it satisfy the first condition? Let's start there. Yes, right? You see, it tells me right here, if I plug in 6, I get a 3. So that means f of c is defined. That's what number 1 is saying. You are able to plug it in. Number 2 is saying, does the limit exist? Well, we just talked about that, right? We said it's the same on both sides. They're both going to 3. So the limit does exist, right? So number 2 is good. Now, is the limit, this is part 3, is this the same as the functional value? Is a limit equal to the functional value? All right, you see what I'm saying? They both have to be 3 in order, or whatever that number is, they have to be the same to satisfy number 3. Since all 3 are good, then we are continuous there. No problem. So that's the basic concept of continuity at a specific point. Of course, they will get a little harder. Like, check this one out. Is this the same from the left and right? C is -2. From the left, from the right, what am I approaching? All right. When I say left and right, I'm talking about the x values, right? I'm approaching -2. So what is the function doing? What is the y value turning into? Right. As I plug these in, I'm getting closer and closer to this y value, right? Does that make sense? So from the right side, the y's are going to 2. As I get closer and closer to -2, the y's are going to 2. As I approach from the left, they're also going to 2. That's why these are 2. Right? And if these are the same, then that means the limit exists, right? If they are the same, then the limit is 2. Is it continuous here? And if not, why not? If so, why is it? Or continuous at c equals -2? Does it pass all 3 conditions?
Would it be not continuous because c is equal to -2, but it's +2 for it's approaching +2 on the left and right?
So we have to look at the conditions, right? Let's see here. I like where your head's at. So we said the limit existed, correct? So number 2 is good. Number 1 is the one we're curious about. When you plug in c, in our case, check it out. And I plug in -2, it's actually defined up here, right? So -2 is equal to 3 because there's a hole here. So it is defined here, right? So far, 1 and 2 are good. But now we have to find out, is the limit the same as the functional value? What was the limit?
The limit was 2.
Yeah, the limit was 2, right? And then we said the functional value is up here, which is 3. Do you all see, and if you don't, let me know, why it fails number 3? Why condition 3 is not working for us on this example? It is not continuous because it fails number 3. Does everyone see why it fails condition 3? You let me know, because this is the time to ask questions. Like, if something is weird or doesn't make sense to you, just let me know. That's what you're here for. Okay. I'll move on I'll move on to number 2 then if you don't have a question. Oh, let me see, Arnie. Yeah, so the limit is equal to 2, right? Or so that's what we found because it was the same on both directions. But when you plug in the number -2, it doesn't jump here, it jumps up here. So the output f of -2 is actually equal to 3. Even though it looks like it should be 2, but it's undefined on purpose. This is basically one of those piecewise functions. You remember? It's like something like this. The triangle would be like something over here, but then over here it'll say, well, when it's f will equal or y or whatever will equal 3 if x is -2. Then over here it'll be everything except -2. So it'll have another equation forming the triangle piece. You're probably gonna have 3 equations, but that doesn't matter. Just know that the function output is not 2, it's 3, but the limit is 2. They're not the same, therefore not continuous there. So that's the theory behind it. That makes sense, or to everybody, to everyone? Okay, let's keep thinking about it. I mean, this is a new concept, so it takes a few tries to make it sink in all the way. So right here, the limit as c approaches where is it? Oh, there it is. C is 1. Like, where the hell is the C? It's right here. Ouch. So as I approach the x value, right? And so it was approaching the x value. So whenever I keep saying approach right and left, what I'm talking about is as the x values go to 1 from the right side, what is your y values turning into? That's basically what we're doing. As I'm coming from the right, the y is going to be a constant -4. You see that, how it doesn't change? And then when I come from the left, it's a constant 4. Notice how these are not the same, right? Since they're not the same, what does that mean? Yeah, there's no limit, right? It doesn't exist. And condition 2 said, right? Condition 2 said the limit exists at C. And if it doesn't, well, it's not continuous at C. So it failed number 2 automatically. All 3 need to be true to be continuous at a point. So as soon as one of them fails, I'm like, all right, well, I already know, not continuous. See, no limit, not continuous. Okay, so that's all the graph problems. Let's look at the ones where we actually got to solve stuff. And don't forget that you can always graph them too. I mean, there's nothing wrong with that. If you can do some algebra like the last section, go ahead and do it. But some of these I would just graph. Check this one. Like number 4 and 5, I'm like, I don't see any technique or easy technique. Ouch. That will let me just plug it in or cancel stuff on number 4. 5, I could maybe use the definition of x minus 2 to help me out. Like these technically cancel. Do you agree that if I'm only looking at numbers above 2, because this is coming from the right, correct? If I'm only looking at numbers above 2, do I really need absolute values? Does it make any difference? You see what I'm saying? Absolute value of a positive is still positive. So does it really matter if these are there? And if I remove them, what happens? This is not a trick question. What is this equal to?
1.
Yeah, it's 1, right? You see how they just cancel out? Yeah, 1 no matter what, right? And if you graph it, you would see that anyway, but you can kind of just reason your way through this and think about it. You don't really have to do any work, but you could. You can also graph it. Let's say we add a function here. Where is that button here? Okay. That was the first, right? X squared minus 9. No, the 3. Let me see. I forgot. Yeah, 9. And the other one was, let's call it G, I guess. So if we look at the purple one, the one we were just talking about, if we're coming from the right, you see how the Y value is 1 the whole time. So if you were to have graphed this, you would have seen that the limit from the right is 1. But analytically, we showed that it would cancel anyway and equal to 1. So both methods is fine. You could also use that third method, the very first one we talked about on day 1, or day 3, actually, technically. You can plug in numbers above 1 and right below 1 and try to figure out what it's going to be if for a regular limit. But for a one-sided, you'd have to plug in numbers closer and closer to 1. So you could only use above 1.001, 1.0001, etc. But anyway, you can see graphically, I think is the easiest thing you could do, unless you reasoned your way through this. On this guy, limit from the left, or yeah, from the left at -3. So -3, I don't know where that is. So let's make a marker. From the negative side, from the left side, minus, it shoots down forever, right? So there is no actual limit. You could say it's negative infinity, your limit, which is fine once we get to infinite limits. But this limit does not exist, or I would also accept negative infinity. Does that make sense? You see how the Y value just shoots out forever. Okay. Alrighty. 6. Let's see here. This is an analytical approach. We can factor the top, the top, correct? Using a difference of squares formula. This top part factors into this. Once it cancels, your F turns into x minus 1. So to discuss the continuity, if x is continuous at x equals negative whatever, okay. Okay then. So this type of, when this happens, is cancellation. This is called a removable discontinuity. So if you can factor and cancel out the problem, because you can see right at the beginning, right? I cannot plug in -1. Do you see what happens if I put in a -1 in here into F? Do you see the issue? Yeah, it's going to become undefined, right? So since I can cancel out the undefined, I remove the whole basically. So this is called removal discontinuity. That's what they want you to understand here. Even though the answer is no big deal, that's the idea they want you to understand. It's also in the videos and the notes. Is there any question on number 6? Number 7, they ask you what type of discontinuity and where is it at. So basically whatever makes it wherever there's a hole or a point you can't plug in or undefined, that's going to be a discontinuity place. Now, if you can cancel out that issue, right? The issue is at 0. If I can somehow cancel this X, then it's considered removable. But there's nothing I can do here to remove it. You agree? Nothing's gonna happen. So it's gonna be non-removable. So just when you do these, just look and see, okay, is there a problem somewhere? And if I can't see it, graph it and then check. Or just ask yourself, is there any value for cosine that I cannot plug in? Is there any value for this particular X that would give me problems if I plugged in some number for the X? You can plug in whatever the hell you want. It's not going to be a problem. And you'll see that on the graph if it's not obvious. So if there's no discontinuity, why would we talk about removable, right? Anyway, but that's the general idea and the concept. Is there any questions on how to find a one-sided limit, like a limit from the right and a limit from the left? Any questions on figuring out if something is, if there's a if a point is not continuous using these 3 conditions here? And that is pretty much the whole concept. 2.4. All right, just let me know. So next week, I'll probably finish chapter 2 and then we'll review for the exam. So this weekend, I'd like you to be caught up with chapter 2 if you're not already. Do you have any homework questions that you're struggling with from 2.2? I'm gonna let you do 2.1 on your own, but any issues with 2.2, 2.3, or 2.4 if you're ahead? You can do any question if you like, if you're struggling. All right, well, if you have no questions, you're welcome to head out. No, the best part of math late at night, you can just fall asleep right after, you know. I'll stick around if you have any issues. If not, I'll see you Tuesday.
Have a good weekend.
You too.